Hello, and welcome to Chemistry Revision video C on AQA Chemistry C1, and today we'll be learning about electronic structure. So if you've watched my last video, you know that we have said that electrons orbit atoms. Now, the number of electrons in an atom can vary according to the proton number, or the atomic number. But you also need to know that the exam board wants you to know that electrons are positioned in certain energy levels or shells. They're arranged in certain different shells, and they occupy certain different energy levels. And yeah, so let's just make it clear that we are learning about electronic structure. Electronic structure. Okay, and let's put that up there. Now, what have we said already? We've said that number of electrons, number of E equals number of P, proton. The number of electrons equals the number of protons? Yes. Now, we have also said that electrons are arranged in a certain way in an atom. They occupy certain energy levels. That's kind of a keyword, or you can call it shells. Now, so we've said that they occupy certain energy levels, and electrons with the electrons with the lowest energy level are closest to the nucleus, which we have said is the central part of an atom. Now, next we're going to talk about how electrons are actually arranged. But first, we just need you to know that need you to know what an electronic structure diagram looks like. So you would have the middle, and then on the outside you would see you see rings, which represents the shells, and then the number of electrons, blah de blah de blah, and that will be what we'll be using for the video. But we'll go through that in more depth. So we've just got a periodic table here of some of the elements we will need to use, and here is what the exam board wants you to know the electronic structures of. If you still don't understand the electron structure, don't worry, we'll go through that later in a few minutes. But here are all the elements you need to know electronic structure of. It's not the actual representation of the periodic table, but it's a shortened version. As you can see, it's group 1, 2, 3, 4, 5, 6, 7 to 0, and it's been shortened down. They've cut the transition metals in the middle away, and they just put it together, and you need to know the first 20 of them, which is helium to calcium. You may need to know about hydrogen, but we've got a hydrogen example later anyway. So, the rules for electronic structure. The innermost, or the first shell or energy level, can only ever have 2 electrons occupying it at most. So that explains itself. So you can only have ever 2 electrons in the innermost shell. So back where we were, as you can see, I drew it with 2 electrons represented by the crosses in the inner shell, and no more than that. And then we also have all other shells can have up to 8. So the higher energy levels that is not the innermost can have up to 8. And if a shell already has 8 electrons, a new shell is needed for the next electrons. So you may not understand that right now, but we're just going to do a demonstration. So beryllium is Be, that's the symbol, and atomic number is 4. So the number of protons is equals 4, and we know that the number of electrons is equal to 4 as well. So we need to use 4 electrons here in this electronic structure diagram. And so what we're going to do is, because we know the first shell, the innermost shell, always has 2, we're going to draw 2 crosses here. Now we've already used up 2 electrons, so 4 take away 2 is 2. We've got 2 left. So we draw another ring. Doesn't matter what colour it is, you're probably using pen at school in your exam. So we draw another shell, and then we've got 2 left, so we can draw another 2. And we'll count up the electrons, 1, 2, 3, and 4. 4 electrons, that is the electronic structure of beryllium. Now, what if it's something more big, more electrons? Let's work with that. Sulfur, we know the first 2 has 2. Well, the first shell, the lowest energy level, has 2, so we have to draw 2. And we have to, a new shell has to be created. So we draw another one. Now let's do the maths. 16 take away 2 is 14. So we have 14 left. Now let's fill up this shell with as many electrons as we can. So we know of all the other shells can only have 8, and let's draw 8. Let's have 8 electrons in the second shell. And we have 8. So 14 take away 8. That is 6. So we still have 6 left. And if a shell already has 8 electrons, we have to make a new shell. So we draw another one. And then we also have 6 left. So we draw 6 electrons. 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Am I correct? So we got 2, and then we have 8, so that's 10, and we add 6, which is 16. And that is the electronic structure of sulfur. S is a symbol. So I hope you have a good understanding of what that really means now. Basically, it's just like how electrons are arranged. So next, we're gonna move on. In this part, the exam board also wants you to know about like alkali metals and noble gases for some reason. So we are gonna do that because that's what it wants us to do, and it's always good to learn stuff. That's the best part of education, you learn things, yeah. Now, alkali metals, group 1. So if we go back to the periodic table, we know that elements are arranged in different groups. And group 1 is these ones: lithium, sodium, potassium, rubidium, cesium, francium, and all that. And the exam board wants you to know, you need to know this, that, let's type this up, shall we? Well, group 1 alkali metals are are very reactive, and there's a reason for that. Now we're gonna talk about this in a brief moment, but for right now, you need to know that it's because they have only 1 electron on the outermost shell, not fully occupied. And that makes sense. It only has 1 electrons on the outermost shell. It's not occupied. It doesn't have 8, but we'll go through that in a second. Not fully occupied. And then they also, and because of the reactiveness, you need to know that it reacts with oxygen and water easily. So, e.g., sodium plus oxygen turns into, where's my arrow? Turns into sodium oxide. And so if you react an element, a metal with an oxygen, it becomes an oxide, basically, specifically an alkali metal. Although it applies for other metals as well. If you react, say, francium, which now let's make it more within your example specifications. Say you reacted potassium with water, then you have potassium hydroxide because it's a hydrogen. It's got hydrogen in it. Water is made of hydrogen and oxygen, specifically 2 hydrogen atoms and 1 oxygen. So the hydrogen hydroxide. Yeah, that makes sense. Next we have the noble gases. Now, what the noble gases are, they are not very reactive. Not reactive. And the reason for that is they have a fully occupied, unlike the alkali metals, they have a fully occupied outermost shell. So what does that mean? Again, we'll go through that later again, but so that means they have a stable arrangement of electrons. So what does this all mean? Well, let's go back here, right? We know the reason that noble gases are not very reactive is because they have a fully occupied outer shell. What that means is, let me just give you an analogy. All elements or atoms want to be as happy as possible. They want to be as unreactive as possible. And what they have to do for that to happen is have the fully occupied outer shell. So this one right here, this one would be a oxygen atom, and it would be always kind of happy, but for it to be like not reactive at all, it would need to have two more electrons on, no, 4 more electrons. What am I doing? What's my mouse doing? It would need 4 more. Wait, no, that's not an oxygen atom. That is a carbon atom. What am I doing? But that's a carbon. It's a carbon. It's not anything else. It's a carbon atom. And for a carbon atom to be happy, has to be fully occupied. So we need 4 more electrons on the outer shell. Now, whereas a lithium, or have we already got one? Whereas lithium has 1 on the outermost shell. That means it still needs 7 more, and that makes it really, really reactive. It will do whatever it can to be as happy as possible, or have to be as occupied as possible, which is what makes it really reactive. So that's why it reacts with things easily, whereas noble gases, they are fully occupied, so they won't react as easily. Next, so we've already represented electronic structure in this way, like this. We draw a diagram for it, right? So we draw a diagram of like the shells, and then the crosses representing electrons. But a more simpler way to show electronic structure would be to just write it down. I mean, say we have calcium. Not calcium. Calcium. We know that calcium's atomic number is 20. And that means it's got 20 electrons. So instead of drawing it, we can write it down as 2882. Basically just describing the amount of electrons in each shell, starting from the innermost, working outwards. Whereas for this one right here, which is also a carbon, I'm obsessed with carbon for some reason, it would be 2, 4, because in the first shell you have 2, next you have 4, and that is a really simple way of describing the electronic structure. And they might give you this in the exam, and they might get you to draw from it, or they might do it other way around and get you to write down the structure. It's really not that hard, but now we've gone through all the things you really need to know. Apart from, if we go back to here, so if we go back to the periodic table, we have already got the groups labeled, so we know that elements of the same groups have same amount of electrons on the outer shell. Now, in the last revision video, I said that elements of the same group have similar properties, and that is all down to the electronic structure. And now you know why. Because of the fact that the amount of electrons in your outer shell determines your reactivity behavior, that means that elements with the same electrons have the same type of properties, same behavior. But as you go down, because we have an increasing number of shells, the reactivity also increases. Now we have the test, the one that everyone's dreading of. So I want you right now. Let me explain this first. So here we have 4 half-drawn electronic structures of hydrogen, boron, sodium, and argon. I've given you the atomic numbers here, here, and that tells you the amount of electrons. And what I want you to do now is pause the video, and then on a piece of paper or whatever, draw what you think the electronic structure looks like. Then we'll go through it. Okay, so pause. And I assume you've paused. And now we're going to go through the electronic structure. So hydrogen has 1 electron. One proton, so it has 1 electron. So the simplest thing to do is draw 1. And that is correct for hydrogen. Simple as that. Might have been a bit confusing, this one, because I said I might have said that the innermost shell has up to 2, but it is up to 2, so you can have 1. So hydrogen is the only exception of having ignore that, having 1 electron in the innermost shell, because it only has 1 proton. If it has 2, then it'll make it negatively charged, and that's not how things should be. Now for boron, hopefully you've that's 5. So if I draw 2 in the innermost shell, 5 take away 2 is 3. Terrible 3. I apologize. My handwriting will hopefully improve when I get my tablet, but as of now. So you got 3 left. So you would be thinking, right, let's draw 3 outer 3 more electrons in another shell. And that is correct for boron, because boron has an atomic number of 5, and there's 5 electrons there, and that's correct. Now we go to the sodium, the troublesome ones, full of shells and electrons. Now, sodium, again, we've drawn 2. 11 take away 2 is 9. I haven't done a calculation working out, but you know 11 take away 2 equals 9. I've drawn it there. So we can start a new shell. And since the max is 8 and we want 9, we can draw 8 already, because we know we'll have 1 remainder. So if we draw 8, then we have 1 remaining. So we start a new one because we have to, because 8 is the maximum for all the other shells apart from the innermost one. And we draw 1 more, and that is sodium. Next we go to argon. So sodium is the It is the alkali metal, and it is very reactive. Hence, there's only one, and that is because there's only got one electron on the outer shell. But argon is a noble gas. Yes, argon is a noble gas, and it's 18. The atomic number is 18. So you start 2. You got 16 left. So you would go 1, 2, 3, 4, 5, 6, 7, 8. So 2, 8, you got 8 left. And that means you have a final shell that is fully occupied. Simple as that. Okay, and here's another point. From looking at electronic structure, you can tell which period it is. Hydrogen has 1, so it's in period 1. Kind of. There's more details to that. But for hydrogen is a special one. But for boron, you see you got 2 shells, so it's in the second period. Sodium has got 3, period 3. And argon has 3 as well, period 3. But that's all for now. And the keywords today, not really going to go through it in detail, but the only new keywords today are energy level, which you should know, which is basically the shell that electrons occupy. Shell, which is basically energy level, but like a ring would be a shell, and then you have electronic structure, which is how the electrons are arranged in an atom. Now, if you have any questions regarding this entire video, feel free to ask them in the comments. If I haven't explained anything clear enough, ask me. I'll try to explain it as best as I can. Now, this part of the video, the end bit, will be me going through last video. Any mistakes I've made, I'll address them right now. Last video, I made an analogy of atoms and electrons to the Earth and the Moon and gravity. Don't think too much into that. I was just trying to say that atoms have a neutral charge. Really, that's all I needed to kind of say. But and also one other thing, gold is AU, not AG. I pointed to AG last time, but gold is AU. And that is all there is to this video. So hope you guys found it helpful. Remember to leave a like, subscribe, and also comment if you have any questions or what you thought I could do better, what you thought I did well. Basically stuff like that, and I'll see you guys in the next revision video. Bye.